All right. Okay, welcome back. So, hope you all had a wonderful long weekend. And today we're gonna have something new started. Okay, so we're gonna talk about support vector machine. And acronym is SVM, and it's actually so speaking from the perspective of nowadays, SVM is a pretty old technique, but it has its own era, like maybe 20 years ago, before deep neural net really stepped on the stage. We have basically the support vector machine as the state-of-the-art models for a lot of for most of the supervised machine learning problems. Like it's basically offers a very standard and off-the-shelf solutions to a lot of problems. Even in nowadays, I don't think we have totally forgotten about this technique, because when you think about when you want to have some quick experiments or quick trials on some supervised learning tasks, it is still something that you may think of using as a quick experiments or as a basic baseline model to compare with. Okay, so the advantage of SVM is that it's based on a very strictly defined and elegant mathematical basis. Okay, so it's based on an idea that is mathematically reasonable, and we will lay out the ideas step by step at the first. So, okay, I see a question here for the last parts of the assignments. Yeah. I'd recommend you that you compute all the matrices, all the metrics yourself, instead of using some confusion matrix implementation. Yeah, in sklearn. So, because I have those lines for you to compute for, like, you basically want to compute what is true positive, what is true negative. Like, these are the tests for whether you can correctly implement the fundamental idea or fundamental concepts. Okay. All right. Okay. So when we talk about SVM today, we will have some preparation to do. Okay, so we need to review some terms and concepts in math. So it's actually some advanced concepts that we need to get reviewed first. Yeah, so there's actually a lot of details behind the term SVM. We need to know what an optimization problem is, and what is a typical solution to an optimization problem, and how do we in mathematics, how do we find the solutions? Okay, and then hopefully we will have time to cover the decision boundary. How do we define the decision boundary that are necessary for the definition of a SVM model? Okay, and then we basically define SVM with the knowledge that we prepared as a optimization problem, and then we try to solve it with the standard operations, with the standard solutions that are typically used for optimization problem. Okay, so I know it's a lot of terms involved, so don't worry too much. Let's get started for the preparation step. So let's look at what a constraint optimization problem is. So it is actually a process to optimize some objective. So this objective function is defined with respect to some variables, and we want to optimize this objective with respect to these variables. So it can remind you of the work we have done for linear regression and logistic regression. In both problems, we have defined the cost function as our objective. It is the cost function that we want to minimize, right? So we indeed had already know what an objective function is, okay? The difference is that previously when we talk about cost function, the cost functions are defined with respect to the parameters of models. We have thetas, w's, b's, okay? So these are the variables that we are interested in, okay? And the difference here is that the constraint optimization problem is that we have some other constraints on those variables. They are not free variables, okay? We cannot have arbitrary values for these parameters. So that makes things a little bit different and much more trickier here. So that's the previous cost function we have defined for linear regression, logistic regression, respectively. Okay, and we have indeed used the gradients method, which is to take the derivatives of the cost function with respect to the variables. And we haven't had a lot of major difficulties because we don't have any constraints, or those optimization problems are not constrained. Okay, we don't require that, okay, your theta or your W or B must within these certain region. No, we don't have that constraints in either previous case for linear regression or logistic regression. Okay, but the problem we are going to talk about today is indeed a constraint optimization problem. So there are several different types of constraints. Okay, so given a constraint, what the usual solution, the typical solution is that depending on what type of constraint is, if the constraint is only some equalities, some like equations placed as constraints, then it's an easier case. So in these cases, we can use the technique called Lagrange multiplier. Okay, or some people sometimes we call it Lagrangian. Okay, Lagrange multiplier to solve it. It's the French mathematician's name. So this type of method usually looks like this. It's a optimization problem. For example, we want to maximize some function. Okay. Yeah, one more thing about the optimization problem. It is not necessarily to minimize. So it can be both either minimize or maximize. Okay, both direction is okay. All right. And we want to, for example, maximize the function f defined on x and w, on x and y. And since we have the constraints that the variables x and y should satisfy this equation, like some g of x and y must equal 0. Okay, so given this condition, these constraints, it means we need to construct some additional functions or additional mathematical expressions called Lagrangian multiplier. Okay, so we can think of the problem as defined by this map on the right, or these plots on the right. If we don't look at the red lines, the red functions yet, we only have the function f of x and y. right? So if it's you can think of the dashed lines as the contours of the f function, right? So eventually we want to find the maximum points where the values f is maximized, right? But now, since the constraint, the existence of such constraint, it means that we must find such a point along this red line, right? Because this equation must be satisfied, must always be satisfied. So it means that we cannot find, for example, we cannot find solutions here. That is not our point because it's not on the red line. It also should not be here, okay? So it only should be along these red lines, okay? Where you can only find the solution along the line, okay? So maybe along this line, the maximum, the value for f is maximized. And after we deviate some steps away, then the values getting smaller, okay? So it gives us some additional constraint to satisfy it, okay? So the typical solution is to use Lagrangian multiplication. Okay. Let's go to the next slide. The intuition behind is that when it is a maximum point we want to find. So at near the positions or at the maximum of f xy, then the function f cannot be increasing in the direction of any neighbor points, right? I think that is the definition for maximum point, because if I go to a different point, I can have a higher value than my current point is not a maximum, right? So suppose that we are working along the contour lines of this constraint function, okay? And the contour lines is basically the direction perpendicular to the direction of gradients, okay? We basically want to find the points where the function f does not change as we work. And that is the point that the maximum point is has reached, okay? For example, this line, okay? So if we walk along this line, walk along that direction, then because it's in parallel with the contours direction, then along that direction, the f, the values indicated by the bluish functions does not change, okay? So that point might be the maximum point, okay? It might be the point that we should stop, okay? So based on these thoughts, okay, the contour lines at this point, the contour lines of the two functions, f and g, should be parallel, okay? And that means the gradients should parallel because contour are perpendicular to gradients. If the contours are in the same direction, then the gradients of these two functions should also be in the same direction, okay? So again, the gradients are just vectors when we have a multivariate functions, okay? In this case, the variables are x and y, then the gradients are also defined on this two-dimensional vector, on this 2D vector. So the gradients for f is like this. It's the partial derivative. It's the derivative of f with respect to the two variables. And the gradients for the g is like this. So we use the constant lambda to indicate the relationship that the two gradients are in the same direction, are along the same direction. They are in parallel, okay? Only when two vectors are in parallel, when we can multiply a constant to convert one vector to the other one, right? Otherwise, we need to make some transformation, right? If the two, so this is the condition that we want to satisfy because this is the place where a maximum can be found. Okay, so remember this form. So we will basically rely on this form to do the next step. And this lambda is something we want to solve in the next slide.
Professor?
Yes.
I think just to better understand this thing, I'm just thinking where the f and g functions are intersecting, and I'll choose the highest value of y where they both intersect. Uh, that is what I thought initially. I mean, that should be the answer. Let's say on this graph where red and blue are intersecting on the outermost circle point, that should be the maximum point for both of them.
Okay.
But this is my first thing. But second thing, when I see your definition about this one, that the both lines should be parallel, can you give a little bit some other example where both f and g are intersecting, but the gradients are parallel and that are not parallel, if that's possible, just to have a better clarity?
Okay. So I think you have misunderstood the function f. So f function is defined on top of x and y. So the value of y is not the value for this function. You can think of the value for function is along this imaginary z.
Okay, got it. Yeah.
So we are actually looking downwards. If we are from have a sky perspective, we are looking forward or looking downwards. And these blue dash line, they are the contour lines of a hill. Okay.
Kind of this is 3D space, but we are putting into 2D space. And
yeah. It's a projection.
The projection, sorry.
It's a projection onto the 2D space defined by y and x.
Got it.
So you can think of these points, these red dot, these blue dots that I'm drawing here. It's the kind of the peak. It's the peak of the hill. Okay, and this red path is, you can think of someone going hiking on the hill. Right, he's going like, when he is going this direction, let me use the, when he was here, the person is going here, he's maybe at the bottom of the hill, and when he goes this way, at this position, he is almost half the height of the hill. And this is the point, the triangle place is where he reached the top up along his hill, because when he goes forward, he will go in downhill again. Okay, so these are downhill positions.
Is this we are supposing it's downhill? If after that it's going down, or we can see from this graph it's telling us that it's
this graph is telling us, because if you look at the blue arrows here, the blue arrows, these arrows, those are the gradients, the direction of the gradients. That points to the maximum place. That points to the maximum of the f function. Okay. So those blue dots, the blue arrows, means that only by working that way, you will observe the increase of the f function. Right. If you go that direction, then there is a decreasing component. The f values is actually decreasing because it's not going towards the gradients direction. Okay.
Okay. And
we assume that this is the maximum value we can get, because this is at this point the gradients of the red function, of the g function, is in parallel with the gradients of the blue function.
Are we assuming that each one of for the function of f, are we assuming that each one of those circular sections are like a shelf rather than like an actual gradual ascension?
I don't know what you mean by shelf. Like, do you mean these circles?
Yeah, like if we were to turn it 90 degrees about what is the z-axis, or like we're looking at it in 3D basically. Each one of those, is that a shelf, or is it like actually like as we go closer to the middle of the circle, like it's actually increasing in value, the function.
Yeah, I think you can think of it as a shelf. So one meaning for this, let me plot this z again. So along this contour, so we call this dashed circle a contour. So all the points on this contour, they have same values for z.
Okay. Okay. Yes.
Yeah. So it's like these. Right now we have three shelves. We have three circles, right? These circles are you can think of it as discrete, but the whole space is continuous. We can add one more circle in between, but it only has relatively different z values. You can think of it that the z is 0 for the most outside circle, and z becomes 1 at this circle, and z becomes this 2, z becomes 3, right? So the value z here is a value of the f function, and the f here is the biggest value. For example, we have 10 here at this near this point.
I see. Thank you.
Yeah, so the purpose of g of xy is that this is our constraint, right? If we don't have such a g, then things are much easier because we just need to work along f. We just take the derivative of f and make the derivative 0. Then we can find the solution where the maximum point is, right? But since now we have such a constraint, we must have this g of x and y equals 0. This is determined by the problem, right? The problem says that we cannot have the x and y's breaking these constraints. Okay, so we have no choice. We have to walk along these red paths, right? For example, there's only these paths along in this hill. Okay, there's no other passes. Then the highest position we can get is this triangle, but not this theoretically maximum point. I hope that analogy makes it easier to understand. Okay, so just imagine you are climbing a hill, but there's only one path you can go. There's no other ways to go. Then you have to find the location that you can find along the path. Yeah.
Just to confirm, so you say where f does not change as we walk.
Mm-hmm.
I feel like at that maximum, if you were to go to the left or to the right, it would change. So are we really just looking for where it's the gradient? The contour lines are parallel. Is that the main thing?
Yeah. That's we are looking at the points where the contours of the red line and the blue dash lines, they are in parallel.
Okay, so
that is our purpose. Yeah. Alrighty, a lot of good discussion here. Okay. The maximum z value where they are parallel. Yeah, the maximum. Actually, not sure what your question is, but maybe I think we should go on to the next slide so we can have the slides finished in time, and any discussions we can put it offline or near the end of the lecture today. Okay. All right. So this lambda is something we called a Lagrange multiplier. Okay. All right. So we can now convert the original optimization problem into the Lagrangian expression. Okay. And the Lagrangian expression is something like this. We put the original function here, and we minus the lambda times the constraint function. The constraint is a equation, so we can put it here. With this Lagrangian, we have additional variable lambda introduced. Okay, so this Lagrangian expression has 3 variables, not just x and y, but also lambda. What we can do is to take the derivatives of the Lagrangian and make the derivatives to be 0. Okay, because this will satisfy 2 two conditions. If you take the derivatives of this Lagrangian, it is equivalent to satisfying both conditions. The first condition is the parallel contour condition. That's the G's contour, the G's gradients is in parallel with the F's gradients. And the second condition is the constraint that we have in the original problem. Okay, so that is some conversion into the Lagrangian expression. So we can use this to solve lambda. Okay, because in this case there are three equations for three unknowns. All right, so let's look at a concrete examples. So again, this is a 3D space. Okay, we have if you look at the x is here, y is along this, and the z is the third dimension. All right, so we are observing some functions f as linear function defined on top of x and y. We want to maximize along this linear plane. Okay, but since we have some constraint, actually, if there's no such a constraint, then we actually cannot maximize this function, right? The maximum value should be infinity. So we have the constraint, which is in this form. And we can actually tell that this constraint is a circle. So x and y should lie on top of this circle. Okay, all the points, we can only choose a points along this circle. Okay, and using the method that we defined in the previous slide, we can construct the Lagrangian like this. We use the original function f to minus lambda times g of x. And the g of x looks like this. Okay, g of x and y actually. All right, given this Lagrangian, we can take the derivatives of the Lagrangian and make them 0. Right, so it's quite easy to do because all the terms, they are differentiable. Okay, we have the first component to be 0, second component to be 0, third component to be 0. Right, and we can easily solve it by getting lambda equals either 1 over square of 2 or the negative of 1 over square root of 2. Okay. Yeah, so yeah, I think Brandon has a good point. So the problem of the local maximum can always be there, and it's related to the nature of the problem. Okay, so if the function, say the shape of f is not a regular shape, it's not a what's it called, a convex function, then it's likely that we are finding the maximum if the constraint we have, the constraint that the paths we have do not go to the maximum, the global maximum. So that is inevitable, I would say, but that's still the best we can get by following the constraints we must follow. Okay. All right. So in this example, we can see that the lambda has two solutions, right? So which basically points to these 2 points. Okay. So these are the 2 points that we want to calculate to find which one is the minimum point, which one is the maximum point. We need to make such a comparison. So, and we have these points here, which is defined by these coordinates, is exactly the maximum points. Okay, so you can think of this problem again as that you are working along this ellipse circle, right? And you want to find the point where the f function is maximized, and apparently it is the top point here that the f is maximized. Okay, so all this simple example is to showcase the Lagrange multiplier is a function that works. Okay, that is actually provides some general solutions to constraint optimization problem. Okay, but yet this is still the simplest case for constraints for constraint multiplication. And a more complex example is the case when we have constraints not in equations, not in equality, but in inequalities. Like if we have such a constraint, and it's more than just one constraint in this example, okay, we have a bunch of inequalities, and actually m of such inequalities, and all of these inequalities needs to be satisfied, okay, while we are minimizing some function f of x here. Okay, so this inequality constraint makes things much trickier, and in this case, it is actually this condition, this problem on the left is actually equivalent to maximize this auxiliary function. We can define the auxiliary function by this. So if the conditions are satisfied, then we let the function to be the original form. If the constraints are not satisfied, we let the function to be defined on infinity. Okay, so this becomes the it's just a transformation of the problem into some auxiliary function. Okay, and then given this auxiliary function j of x here, we can define we can further use some indicator function here to help define the function of j, and this indicator function is defined on either 0 or infinity, depending on whether the expressions of the function's body is satisfied, is lower than 0 in this case. Okay, all right, and because this I is non-differentiable and discontinuous, we can use a lower bound on a lower bound of it, which is a linear function lambda of u. So this is something very advanced called Lagrangian duality. Okay, if you are interested, I would recommend you to read the whole resources here. But the point of having these seemingly unrelated auxiliary function defined is to help us to construct another Lagrangian. Okay, we need to get the Lagrangian in this form. We can define the lambda for each inequalities, because now we have a bunch of constraints. We actually have m constraints. So for each constraint, we can define a Lagrangian called lambda I. Okay, and we use the function within the inequality constraints as part of the term here. Okay, so now we have this problem, which is to maximize the Lagrangian with respect to lambda. That'll give us the auxiliary function. Okay, because when all the cases are satisfied, right, then when the Lagrangian is maximized when the lambda equals 0. Okay, because we want to eliminate those negative terms. And if all the constraints are not satisfied, then for some i's, for some conditions, for some inequalities, these constraints is satisfied, then we can set those lambda I to be negative, to be infinity, so that the whole Lagrangian is infinite. Okay, so that this thing on the right is equivalent to the j of x that we have defined at the first place. Okay, so we kind of turn the original goal into a different problem. We want to minimize the auxiliary function, which is to optimize the Lagrangian. Okay, so because you see there are two optimization steps. First, there is a maximize with respect to lambda, and we have the original goal to minimize the auxiliary, which is from the minimization of the original problem. So putting these two opposites minimization requirement together, we can have a minimize and maximize problem. We basically define the problem into some convert the original minimization problem into a mixture of minimization and maximization problem defined on top of the lambda. Okay, and this lambda is exactly this form. Okay, it's similar to the form that we construct for equation-based constraints. Okay, so actually, understanding why this is the case will not be tested in this course, because this is a very advanced constraints optimization techniques. But all we need to use when we later define a support vector machine problem is that the target function that we want to minimize in an SVM problem will be eventually optimized to use this minimize and maximize problem. Okay, so that means we will first maximize the Lagrangian with respect to lambda. Okay, that will give us some results, and on top of that results, we will minimize the Lagrangian with respect to x. It's in two different directions. All right. So solving such a complex Lagrangian optimization problems is actually requires some well-defined algorithms. Okay, some optimization algorithms, and so the algorithm that we gonna particularly use in the case for solving this minimize maximize problem is and particularly for SVM, depending on decided by the nature of the target function, we will need to use some algorithm called quadratic programming. Okay, because the objective function in SVM is a quadratic function, and the constraint is a linear term. So we can use a quadratic programming algorithm to solve the optimization problem. So all we need to know that is the general form for the objective function is like this, right? We can, so in this case, the x are vectors and the q are is a matrix, and the c is also constant. The q and c are the constants. Okay, so this is our target function we want to minimize, and we have a bunch of inequality constraints. Okay, so these a, x, b, they are all vectors and matrices. So given this general form, we can have these constants as the inputs to a quadratic programming program or algorithm, and the algorithm will be able to output the x that minimize the objective. Okay, so the simplest case is that, for example, we can think of the simplest case is like our f function is in a 1D dimension is a simple quadratic function. Is a simple quadratic function. Okay, x like x squared plus 3x plus 1. So if we think of it in the 2D in a 2D space, it is something like that. Right. So, but because we have some bunch of linear inequality constraints, which means we cannot go to all possible values. We have to, for example, only look at one side of this linear equation. Okay, so in this linear equation, how do we find the minimum points? Right? How do we find the minimum points of along this along these quadratic functions lines. Okay, so this type of optimization problem will be solved by the quadratic programming algorithms. And actually, it is not our task to design such a quadratic programming algorithm. All we need to do in this chapter, in this SVN chapter, is to define the target function here. Right. All we need to do is to know how the objective functions are defined, how the constraints are constructed, and then we're able to solve it with some existing algorithms. All right, that's quite a bit of contents as a preparation, but I think these are all necessary preparations for defined the support vector machine problem on a solid ground. Okay. If you think necessary to read more materials, you can follow the links that I provide in the slides, particularly for the Lagrange duality method. When the constraint is a inequalities, then how do we construct a Lagrangian, and how do we come up with this minimizing and maximizing problem? All right. Okay, so I think it's time to talk about support vector machine. Okay, a little bit background. Was first invented in 1995, and it's still, as I said, it's still a commonly used first choice to try out some simple baseline models. Okay, and the idea is also quite straightforward. It basically considers the classification problem as a process to decide the decision boundary. Imagine we are trying to draw a decision boundary to separate the two classes, okay? And we've got two features, x1 and then x2. We try to separate the two classes. So the decision boundary here can be a linear line, okay? And the linear decision boundaries are determined by those coefficients W1, W2, and B. Okay. So how do we find the decision boundary? Actually, when we train a logistic regression model, for example, we are actually drawing a decision boundary, right? Logistic regression is just one way. It's just one method to find the decision boundary. And the threshold taken by logistic regression is to learn the parameters that minimize the cost, okay? And this minimization of the cost function also maximize the likelihood of the data, okay? So anyway, the resulting decision boundary is just W and B, so it's just a linear line. And when on the one side of the linear line, we must have the inequality to be greater, the linear combination W times X plus B must be greater than 0. Okay, on the other side, it must be smaller than 0. Right? That's something we learned, right? Because these are the inputs to the sigmoid function. And when the input is greater than 0, then the sigmoid will output some probabilities that's greater than 0.5. All right. So that is what we learned from the results from the resulting model of logistic regression. Right. But we have a different thought here. Another way to think about how to find the linear separation is to look at the relationship between the boundaries and the nearby data points. For example, this one is definitely some boundary that works, right? We can separate the two by looking at the boundary, right? And I put two dashed lines to indicate how close this boundary are to the most nearby data points on both sides, right? It's actually a quite narrow area, right? So the data points, the most nearby blue one and the most nearby yellow one, they are quite close to the decision boundary, which makes things quite risky, right? When you draw a boundary that is very close to the two sides, then you're probably more likely to make mistakes. Then as a comparison, on the same data, right, all the data points are in the same shape. If I draw a boundary here, then the distance from the boundary to the most nearby data point seems larger, okay, which makes a boundary a safer boundary, okay, because the boundary is clearly showing the gaps. And ideally, we want to put the boundaries in such a position, right, in the right plot, in which the distance from the most nearby data points are maximized, right? And in this case, we say the gaps or the margins between the boundary and the most nearby data points are maximized, okay? And only in this maximized margin case, we are we feel safer, right? Because it's less likely to make misclassifications. Okay, for example, if there's a new data points appearing here, then we are still making the right classifications, right? What if there's a data points appears here? Then, from visually speaking, it's closer to the blue data points, but the boundary will tell us, okay, it's on the same side as the yellow ones, so it should belong to the yellow class. So we're more likely to make mistakes. So I think this is a quite straightforward thinking. Okay, the larger margins means better performance of models. Okay, so now the question becomes, how do we find the parameters? How do we find the W's that maximizes the margin? That is the problem here. Okay, so we get some point to start from, which is good. Okay, so let's take a further step. Okay, how do we maximize the margin? Okay, so these two plots are still to showcase why larger margins is a preferred choice, because you can see that when the margin is too small, it's very likely to make misclassifications. All right, let's lay out some notations to define the margins, to define the distance from the data point, from the most nearby data points to the margins. So we will use 2D data in this case, because I think it's easier to get visualized, right? When you think of a margin in the 2D space, it's just a line, right? It's easier to compute, easier to write down the equations. All right. So when you write a line in the 2D space, it's like this. You've got the two coefficients, W1, W2, and the B. B is the kind of the intercept. Okay, and for 3D, then the decision boundary is a plane, right? A plane. When you have a plane, then you need to use three variables to define it, right? You need to have three coefficients from W1 to W3 and the B as well. Okay, it's like this in 3D space. Okay, and then for higher dimensional data, if you think of the parameters as a parameter, as a vector here, W transpose is a parameter, and the data is in X, then you actually are defining some hyperplane because it's more than 3-dimensional, so it's hard to visualize. Okay. Some other notations. The data has X and Y. Y is the label. And this is basically the same convention that we followed, but the only difference is that now the label is not 0 and 1. Okay, it's not an essential difference, it's just the two categories, but we find that in the case of SVN, we find that when the label is -1 versus 1, it makes things easier. It makes the equations easier to define. All right. Okay. So next, here comes some important properties. First, because if the decision boundary is decided by this equation, W transpose times X plus B equals 0, then for all the data points, ideally, if the decision boundary is defined, then none of the data points should be on that decision boundary, right? That is ideal case. We don't want the decision boundary to go across any data points. So that's why the absolute value of this equation, WT transpose times XI plus B, should be greater than 0. Okay, because otherwise, if it's equal to 0, then it means the data points XI is on the decision boundary, which is not what we want. Okay. All right. So this is the condition we must have. So if we draw it on the 2D space, it's something like this. Okay. All the data points are on the two sides. Okay. There's no misclassifications. That is a ideal case we are defining here. And the decision boundary. So what the question I've got here is that if the boundary is not separable by a linear boundary, then we need to have some tricks. So in this case, we start from the linearly separable data. Okay. That is a good point, but we will see that after we have built a SVN that can separate on top of the linearly separable data, then we can improve it by using some other tricks, like the kernel tricks, like the soft margin tricks. Okay. Yeah, we'll take a step to several steps to that point. Okay. So let's stay on this slide. So if we observe the two sides of decision boundary, we should see these quantitative relations. First of all, the decision boundary is like this. And on the one side, the data points xi, if we apply the equation to data points, then it must be greater than 0. It cannot be 0. Okay. And on the other side, because this is a different class, it is a class for the y equals -1, then the sign of this equation should be negative. Okay, that is a distinction between the two classes. All right, so that also means we can write the equation to like this: y times the linear expression is greater than 0, and on this side, the yi times the linear expression should also be greater than 0. Okay, because that is exactly the condition here. Okay, that's several notations. So here we are facing a problem. A plane can actually have infinite number of representations. I think that is easy to imagine. For example, the plane in this form can also be expressed by this form if we multiply 2 on both sides, or multiply 100, 1,000, 1,000,000, right, on both sides. We can have infinite number of representations. So infinite number of possible parameters. So there's no way to find a unique representation. But we indeed want a unique representation of the plane, right? So that means we need some additional constraints. There shouldn't be just the current constraint is not sufficient. Okay, so the additional constraint that we consider has something to do with the nearest data points. Okay, so for example, let's the x superscript k to be the nearest point to the plane. Okay, and we can place the normalized constraint. So to that nearest point, xk, when we plug in that nearest point to the linear expression here, we let the absolute value of this linear expression to be 1. Okay, this is our constraint we arbitrarily set. The 1 is arbitrarily chosen because it makes the whole computation easier. Okay, but this constraint is a valid constraint because it satisfied the previous constraint here. Because for all the data points, we must have the absolute value be greater than 0. Okay, then for the nearest points, it's one of the data points, and we give it a stronger constraint. We ask that its value must equal to 1, so that now having these normalized constraint here, the representations for the decision boundaries are now fixed, are now a unique representation. Okay, so for example, in the case here, when we take the nearest points out, in this case, it's this blue one and the yellow one here. We arbitrarily define that the yi times this linear expression should be 1 for these 2 points. And we can distinguish the 2 nearest points with the rest of the points. The rest of the points, they must satisfy that they are greater than 1. Okay, not just greater than 0. They must be greater than 1. Okay, because the 2 nearest points, they equal to 1. Okay, so a little bit additional constraints. Let's see what we can get next. Okay, so that now the representations of the decision boundary is unique. Okay, which is good for us because the boundary is unique now, which means we can measure the distance or measure the margins between the point to that decision boundary. Okay, so in order to find the boundary that maximizes the margin, we need to find the parameters WBs that maximize the distance between the nearest points and the plane. Okay, so it's a geometric problem now. We want to find the plane that maximizes the margin from the nearest point, from these 2 nearest, from the margin, from the decision boundary to the 2 nearest points here. Okay, so it becomes a geometric series, geometric problems. We want to find a way to measure the distance, right? We want to measure this distance. What is the distance between the nearest point to the decision margin, decision boundary? Okay. All right. Let's look at this general question. How do we find the distance between any point in space and the plane? Right. Think about that. We basically need to make the projection, right? We want to find the projection of that point to the plane. Okay, so to such a plane, W transpose times x plus b equals 0, then the vector here, the vector W, is actually perpendicular to the plane. How do we know that? Like in this case, in a 2D space, the plane is like x1 plus x2 minus 1 in this case. And we know that W1 is 1 and W2 is 2. So if we plot the vector 1, 1, it will be pointing to the right, to the upper right corner, upper right direction, right? So this direction is perpendicular to the plane, right? That's something we can observe. So for an arbitrary plane in this form, what we can do. So we will prove that. We will first prove that the W is perpendicular to the plane. We can take any 2 points on the plane, which is x prime and x prime prime. Okay, we have 2 randomly picked points on the plane. Okay, we all know that they satisfy the linear expression because they are on the plane. So the linear expressions equal 0 to both points. All right, so if we subtract the 2 equations, we will have W transpose times x prime minus x prime prime equals 0. Okay, so what is x prime minus x prime prime? It's a vector that points from x prime to x prime prime. And the dot product between the between the vector x prime prime and the vector W is always 0. That means the W vector is perpendicular to the plane, right? Because the x prime and x prime prime, they are randomly chosen. There can be any points on the plane. Then any points on the plane, then that means any vector on the plane is perpendicular to W. So the W is perpendicular to the whole plane. Okay, so that is something we will use in the next step. All right, now we can put the W here to indicate the direction perpendicular to the plane. Okay, now let's compute the distance. Because remember, our goal is to compute the distance that is outside the plane to the plane. Okay, so given this xi that is outside the plane, what we can do is to first take any points on the plane, for example, here x, and we can simply compute the projection of the vector from xi to x onto W, right? We can have this black arrow, the vector indicated by this black arrow. We project this vector onto W, and W is perpendicular to the plane. So the length of this projection normalized by the length of the W itself would be the distance from xi to the plane, right? It's the very basic geometric computation, right? What we need to do is to compute these lengths. So it's just the projection of this black vector onto the direction of W, right? And the normalization is necessary because the W is not unit length yet. Okay, so we can rewrite the whole thing into this form. We will basically distribute W into the 2 terms, right? W is here and W is here, and we give each a B. We have plus B minus B, right? That's just some mathematical tricks here. And then because x is a point on the plane, so this whole term are gone, right? Any points on the plane must equal 0. So this whole term are gone. So what's left is just xi, is just the linear expression of xi, okay, divided by W, okay, by the norm of W, okay. So now let's think about the additional constraint that we set previously, because in order to make the representations of the plane unique, then we need to have the special constraint that the nearest data points when xk is the nearest data point to the plane, then what is this? So the absolute value for this one is 1. Remember our conditional, our additional constraint, right? We arbitrarily decide that for the nearest point, this absolute value should be 1. Then the distance, the expression of distance is further simplified into 1 over the norm of w. Okay, so it's really simplified now. It's a really simplified function, objective function. So the whole problem now becomes that we want to maximize this quantity. We want to maximize the distance so that the margins of the distance of the margins from the decision boundary to the nearest data points is maximized. All right. So remember this goal here. We want to maximize this distance. Okay. So maximizing 1 over the norm of the constraints means that we want to minimize, right? Because we want to maximize 1 over this norm. And the norm is just the dot product, the square roots of the dot product, right? So we are basically minimizing the dot product, which is W transpose times W, okay? And also remember, we have a bunch of the inequality constraints, okay? So to all the data points, the linear expression should be less than or equal to, should be greater than or equal to 1, okay? Because only the nearest data points is equal to 1. To other data points, the absolute values should be greater than 1, okay? So the constraint becomes this. The y times this linear expression should be greater than 1. We have that many constraints. M is the number of data points. So if we have 100 data points, we need to we need to have 100 constraints inequalities. Okay. So that is basically how we formalize the problem for support vector machine. So I think I will stop here. You can take some time to look at how to go through this again, of how we define the problem of distance between the nearest data points and between the nearest data points and decision boundary. I think one point that is sometimes a little bit confusing is here, because we placed this additional constraint, normalized constraint. So this is totally arbitrary. Okay, this is something we must have. Okay, it can be 2, it can be 3, it can be other values, but becomes 1. It makes the whole equation, the whole mathematics much more neat. Okay, but starting from these normalized constraints and from the geometric knowledge that we have, when we compute the distance from a point outside the plane to the plane by making projections, we're able to define the distance from the outside point to the plane into some very simple equations in this form. Okay, and this is exactly the objective function that we want to maximize, or it is the norm of W that we want to minimize. And the norm of W is no different than the dot product between the vector W vector and itself. Okay, so eventually we want to minimize this objective function, but we need to keep the inequalities as our constraints. Okay, because for the for all the data points, we must make sure that they are not on the decision boundary. Okay, we have such a big constraint here, and we have to use some Lagrangian duality technique to solve such a problem. All right, that's so much for today. I like to take questions here if you have further questions. All right, so yeah, we find a normal vector pointing from the plane to the closed data points. How do we know when we find the midpoint between the? So it's not a normal vector here. So the W is the parameters of the plane, and the W is a vector. That's true, but it's not a normal it's not a normalized vector. How do we know when we find a midpoint between the two closest? I don't actually know what that means. A midpoint. Do you mean a midpoint between the two closest? Yeah, so sometimes I see what I mean, because in the example that I show, there's one nearest the data point on each side, the blue one, the yellow one. So in that case, the biggest the maximum margin should be the plane right in the middle point, right? But it's not necessarily true, because there could be more data points on one side. There could be one blue points on one side and only one yellow points on the other side. Yeah. So in those cases, it's not necessarily the midpoint.
Professor, what is W? Is it any other point?
W is the parameters that we define the boundary.
Okay. So here XW is slope, right?
Yeah, you can think of W as the slope. Yeah.
Okay. But the dot product of two slopes, if it is 0, then it's parallel, right, and not perpendicular.
Which dot product are you talking about here?
I think it's slide 17, the previous slide.
Okay. Yes.
So, oh, it's W transpose. Okay.
Yeah.
Okay.
So
Okay.
double transpose is just a grammar to put a column vector into a row vector.
Okay. So if the dot product is 0,
Uh-huh.
that means they should be parallel, right, and not perpendicular.
Yeah. If the dot product is 0, that means W is perpendicular to this vector.
I mean, it is because. Okay, I think there is something. Is it because we are using transpose?
Yeah. Oh, yeah. So the transpose means is to make this dot product valid. So of course you can write W dot X prime minus X prime prime. That is also a valid expression, but because we want to align the dimensions. So if W is say W is W1, W2, W3, right? So if that is how W looks like, then in order to make a valid dot product, you need to put it into a row vector, right? You need to write a W transpose. Okay. Transpose
Okay.
just change the shape of the vector.
Okay, I think the answer is in someone gave it in chat. I think that was I asking for.
Okay.
Is it correct? I mean, if it was W, then it would be parallel, right?
You mean if you use the dot here?
I mean, if it was not transpose, if it was just W.
Oh, it was just well, technically speaking, I don't know. I'm pretty used to the transpose notation because it's more strictly defined.
Okay.
If it were just the W not transpose, so I think we should put the W transpose there.
So to make it work for dot product, right? I
Yeah,
mean,
yeah.
dimensions. Okay.
Yeah.
Okay, thank you.
No, the transpose is not a project 90 degrees. No, the transpose is just to is not changing the directions. The transpose is just a operation that makes a column vector into a row vector in this case. Yeah, it just changes the shape of the vector. It's not change the geometric properties of the vector. It's not changing the directions where the vector points to. Yeah. All right.
I think, can you hear me?
Yes, yes.
Yeah, I don't remember actually, but I think the dot product is A dot B is product is AB cost theta, cost theta, which is the degree between them. So when we say A dot B is equal to 0, that means cos theta is 0 and cos theta is 0 when theta is equal to 90 degree. That's where it is coming, I think so. The answer to this question, why A dot B is 0 is perpendicular because there's a cos of cos theta is 0 that time.
Did you say cosine?
Yeah, cosine, yeah.
Oh, cosine, yeah. I think you're correct, yeah.
I think that is the answer she's looking for maybe.
Okay.
I was gonna say, I think it's just dot product is 0 when two vectors are perpendicular.
Mm-hmm.
Yeah, the same thing, yeah, cos.
Mm-hmm. Okay, so yeah, heard a lot of useful discussion here. So I think the content today are quite important. So hope you spend some time on it, and I will release the quiz. So yeah, so I think the SVM is not a easy concept to grasp at once, but starting from this simple SVM based on the linearly separable data is a good start. And on the next lecture, we talk about more advanced. We'll first solve the optimization problem yet. We're not clear about how to solving it yet. So we'll in the next lecture we'll first solve the optimization, constraint optimization, and then we'll talk about some more advanced tricks. Yep, that's it for today. Everyone, take care. I'm gonna stop the video recording.